This is ODL lab number 5, and today we are going to talk on the experiment number 4 over here. And certainly, before I move on towards the actual experiment, this over here in picture you can see the overall PCB, and one problem which I will show you just now. If Ateeb is there online, November 16, kindly unmute your mic at that particular time when I will ask you, and hopefully then I can actually, or maybe you can write down the comment there. Okay, you can see I have soldered this PCB. From the back side I actually showed you. Meanwhile, I will also update on the WhatsApp group or the MS Teams also the actual picture. This one at present, as you can see, is the same PCB which Ateeb has made, and I have soldered that dip switch and all that stuff over there. And don't get troublesome with this one, because where the mouse or cursor is at present, these fours are not actually because of the IC. Actually, I had not that size of bed over there, so that's why I have placed a little larger size with cutting their legs over there. So don't confuse over there. Otherwise, the 1 kilo ohm resistances are also there. These are 180 ohm resistances over there. This is a capacitor. This is that 7805 regulator. I will give you the 3D picture also of this one, but some angles as well. This is actually the top view at present. Now, you can see where my mouse is at present, the orange color one. This is the positive supply, this is the negative. The block connector is also placed over there. This is that ULN2803 IC over there. Now, what I am going to do over here to show you, I am actually going to turn off these 5 displays, 1, 2, 3, 4 and 5. So now these switches are also in the off position. These switches are also in the off position. So when I am going to actually power up this up, only this LED is actually going to turn on, and the displays are not going to be turned on. So I'm just going to plug it in. I hope everyone can hear me out. Please just confirm me on this one. I hope, please just write down in the conversation window that you can hear me out. Okay, thank you. So I'm just plugging it in, and okay, I have given it approximately 8.3 volts. So you can see this now. The green colored LED is working, and certainly those of you who maybe have a issue, maybe it's 5 volts or not, I will show you that 5 volts also. So a little bit hardware mode today, so that you can have an idea what I am actually. Okay, okay, so you can see I have the multimeter over here with me, and I'm going to show you. I have this red color probe and the black color probe over there. I hope you can see the meter very carefully. I am holding my black color one in my right hand, and certainly I am going to put it. First of all, let me check the input. So what is the input at present? So when I just plug it in, you can see this is approximately 11.20 or 11.3. It's actually varying because my power supply is not that very good. So it's 12.2 or something like that. It's still high, but our regulator can actually withstand that, so not an issue. In fact, I can just lower it a little bit. Maybe little bit. So now I just lowered it a little bit, and now you can see it's still 11.3 or 11. Anyway, so now let's check the output of the voltage, that is a regulator. Now, since I know, because I have seen the Mr. Ateeb circuit over here, so when I will plug it in over there at this point, this will show me that it is showing me 5 volts over there. It should be 5 volts, while it's not. It's actually getting a little higher on there. Let me just plug it in. Let me just set the power supply here. Okay, so this is my 9.04, and here this is I don't know why, actually maybe my DC meter is okay. There is a problem with my meter actually. Just let me just check. It's so I have this, let me just check on 8.55, and okay, so this is this point. So I have the input voltage over here, sorry for the delay. You can see this is approximately 8.8 from a power supply, and when I want to check the output voltage from the regulator, which is certainly being applied to the LED, and that is here approximately. So you can see approximately it is 4.90 volts approximately. It should be 5 volt exactly, but anyway 4.9 is still enough for its working. And if you want to check any of the ICs, if you are getting that same voltage on any of the pins over there, so I'm just going to touch it over there. You can see it's 4.92 over there. So I have almost all of the circuit being supplied with that 5 volts over there. I will come on this hardware stuff and all that, how a meter is actually going to be used. We will have a dedicated session for that. Don't worry on that one as soon as we have that. Okay, now I am now going to show you that what is the input. You can see what is the input over there. It is off. All of these 4 are off. If I want to give a data, I am going to give on this male header. These are 4 pin male headers over here. So I am giving it 0, 0, 0, 0. So this means all the binary data is 0, 0, 0. Now if I will turn on the first switch over here, what will happen? The first digit should be turned on, and you can see it is turned on. And what is displaying? It is displaying 0. And if it is displaying 0, this is actually binary 0, 0, 0, 0. So if I will change, let's see now, if I will change this first switch over here, now when I have changed this first switch, it has not displayed 1. What it has displayed 2. Now maybe there is some, let me just check on the other one. What is this? This is 4 has been added. And if I turn on the next one, it is totally off. Now I told you specifically that you are going to arrange this male headers and the bits in equal or least significant bit to most significant bit order, which meant it that the least significant bit was here at 1, then the next, then the next, and then the next. So this was 1, this was 2, this was 4, this was 8. And I hope you remember what I mean by this 1, 2, 4, 8. So what is happening over here, when these are all off, certainly you are applying 0. But when I will turn on this one, this is actually the second. It's not the least significant bit. So Mr. Ateeb, if you are listening me, what you have done over there, you have actually connected the second one over here, and the first bit is here. So your first bit is here, the least significant bit, then the next one is here, and then this is the third bit, and the fourth bit, as you all know, because this will become a 2-digit number, so it's not being displayed. So if I will turn off this one, this is 7, and if I want to show 8 supposedly, then I have to turn off these all and only on this one. This is 8. And since all of the rest of the circuit is okay, this is the second. I have turned on the second switch. I have turned on the third. Now there is a little difference over here. Why this is the difference over there? Actually all of these are having a different make. I actually asked some of my, some student to actually buy this from Hall Road. So maybe he has bought 3 or 4 different types of segments over there, maybe not from the same shop. So that's why you are seeing different illuminations over there. Yes, the resistance is over here, as you can see where my pointer is moving. This is having equal resistance, so there is no difference of actually current. The difference, as you can easily see, is actually the C. These two are very same, these two are again same, and this one is actually, you can see the size is also a little different. But anyway, I would just want to demonstrate it. So if I now turn this off, you can see this is 0 being displayed. Now I know this is 1, so this is 1 being displayed. I want to show now 3, so this is 3 being displayed, and I have now this 5 being displayed, or if I want to display supposedly 6 over there, so I will have the 4 and 2 added, so this is 6. So you can see just by dip switches. Now practically, those of you who have still not understood what I meant by multiplexing, now listen this very carefully over there. I have this 4-bit data. Yes, certainly Atif has done a mistake over here. So when you are going to connect this to microcontroller, you have to take into. Now, normally you as engineers, whenever you are going to present any data to someone, that data is going to be, has to be from least significant bit to the most significant bit. So certainly this has to be in such a way that this is the least significant bit, this is the most significant bit, and this works okay. But here, Atif has done a problem over here. Least significant bit is here, then the next one is here, the next one is here, then the next one is at this position. So what he has done is actually not taken care at this point, because this was the nomenclature at this IC over here. Anyway, you are going to give 4-bit data over here. Now when you are going to give 4-bit data, how you are going to do that? Supposedly you wanted to display something 1, 2, 3, 4, 5. How you are going to display it? Now, since instead of turning on this switch, I can give a 5-volt signal at the first pin. So what I will do, I want to display supposedly 1 here. So what I will do, I will turn on this switch. Okay? I have given now what happened. I have given the data 1 over here. So what I will give, I will instantly give 5 volts at the first signal, which means I will turn on this one. So what will happen? 1 will be displayed over here. Now since 1 is being displayed over here, so what I will do, I will turn off this display very fastly. Then I want to display supposedly 2 over there. I will have given 2 data, and I will turn on the second switch over here. Sorry, 1 is not turned off. So 2, and then I will again turn off, take off the data which I have given, and now this time I want to display supposedly 3. So I will put in 3 on these pins, and I will turn on the third. Okay? And I will repeat this one for 4 and 5 over here. Now this whole process of displaying 1, 2, 3, 4, 5 through this 4 pins and this 5 pins is going to be done in such a fast speed that there is going to be displayed for a human eye instantly. They are not going to be in different cadence. So 1, 2, 3, 4, 5, a human eye is actually going to see like, okay, 1, 2, 3, 4, 5, and certainly a point where you are going to give the point. This is the male header point over here. So you are going to give a 5-volt signal at any of these 2 pins, and you are going to have a display of either point here, 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 depending upon at what point you are giving 5 volt. Now if I give a 5-volt signal continuously over here, this display, this dot, this dot, this dot, this dot, all of them would be on. I will give you a video on that one also through a microcontroller. Hopefully by today evening I will give you, because I just soldered it just one hour ago. So you can see now, you can display any data, 5-digit data with a decimal point on this PCB. Atif has done this mistake. I hope any of you have not done this mistake. Maybe my mistake also, I did not give a full thorough design over there. Yes, Atif's design is the minimum over there. He has done a very good work overall. The PCB was also done good. It's had wonderful size. You can see the actual PCB size is here, is only this one. The rest of the area I'm just going to cut it off, and I'm going to take more pictures of this one. I will cut it off with a saw. So over here you can see that the size of the PCB and the components which are placed on it, there is no empty space. And it's, if you give it to some, maybe some industry, and they are producing some one single layer PCB, this is a 10 on 10 PCB very easily, unless and until you don't do this mistake of this bits which we have done Ateeb over here. I hope Ateeb is listening, and he must be a little bit ashamed over here that he has done this mistake. I hope many of you have not done that mistake. I was checking the assignments last night, so hopefully I will give that result also, hopefully by tomorrow or maybe day after tomorrow. So I hope any questions over here, please write down in the conversation window. You have the circuit in front of you, it's running, and let me just turn on something. So I can just turn on maybe like some of the displays. You can see 333 is being displayed on 3 digits. And any questions, Ji? Any questions who have and don't understand this, how this is working? For those who have who don't have an idea on this one, the experiment circuit diagram was this one, and this is the circuit running here in front of you. This was a circuit diagram over here, and I told you at that time also that D0, D1, D2 and D3, they should be in a straight line, because when you're going to give data now, when whoever is going to now plug in the data, he has to take care that D0 is here, D1 is here, D2 is here, D3 is here. So the sequence is changed a little. Otherwise, it's very same. Okay. Yes, that's a very good question on 136. Question over here is it when you are going to make this PCB, okay? And hopefully I am going to tell you the scheme also, that how these PCBs are actually going to come to you, delivered to you at your homes. You're going to take the toolboxes and all that stuff. I have given over here how much voltage, 7, 8 volts, 9 volts maximum. And the circuit is only taking, let me give you a picture, it's only taking 70 milliamperes of the current, because only some segments are running and only 3 are there. If I turn on all of them, maybe the current is a little higher. Yes, it goes on to something like 85 or 90. Now, when you are at home, and since you are just first year students, you don't have an idea about microcontrollers. Okay? So you are not going to do the coding, and you are not going to actually run it through a code. So these dip switches are there for your checking of the circuit. You can just give 9 volts maybe from a power plus battery, 9 volts power plus battery. I don't know how many of you have an idea. Those 9 volt batteries, simple rectangular shaped over there. You can easily plug in the data over here at plus negative. Of course, take care that plus is where, negative is where. That has to be done very carefully. Your PCB is done, soldered. You can just plug it in plus minus 12, plus minus 9 volts. Plus minus 11 volts, something like that, and the circuit is turning on. So those of you who are asking me in the very start that how you are actually going to find out that your PCB is working or not because you have not worked on it physically, I am telling you that these dip switches are there so that you can actually understand what is happening over there. Now when these PCBs will come to me, I will select some of the PCBs, and those who are running, most probably I will run them on a microcontroller, and I will check it out that are they working correct. So dip switches are there just for your understanding and checking, because you're not going to have the microcontroller and all that stuff. If you were at Maker's Lab, certainly I have those modules over there. You can just plug in over there. Those dip switches were not required there. But since you are at home, and still even if you were at hostel or something like this and you wanted to test your circuit, so dip switches come in handy in such situations. So I could have just put male headers and asked you, okay, you can take a wire from here and plug it into 5 volt, you can take a wire, but that makes things messy. So I have put dip switches. They're not that costly. I guess this 4-bit dip switch is not going to be more than like 10 or 12 rupees, or maybe like 8-bit switch is not going to be more than like 15 or 16 rupees. So you get a lot amount of advantage by using these dip switches. So I hope I have answered this question. No. Beta 136, your capacitor is not going to make it on. What is happening? The regulator is going to regulate the voltage at 5 volts, okay, which is certainly at 4.9 at present. Maybe the regulator is also not that very good because I just took it in a hurry from somewhere else. So capacitor is there so that it can provide that initial or spike current whenever this is going to be turned on. So capacitor, I don't know how many of you have opened the data sheet of 7805, but if you will open that 7805 data sheet, you are actually going to see a lot amount of details over there. That 7805 requires an input capacitor, also an output capacitor. Now I have not installed an input capacitor because I am providing this supply from a power supply. So it has already some input capacitance over there. So I have only installed output capacitor, and I guess if I'm not wrong, I just took this capacitor from the maker's lab. This was approximately, I guess, 470 microfarad or something like that. Those of you who have, I will just give you the whole picture of this 3D picture also. I will take some illumination of all these pictures. You'll get an idea that what I have made it on this PCB over here. Any other questions? Can we switch the connections of ULN2803 to 7 segments? What do you mean by that, beta? Roll number 163, as far as Proteus is concerned, not today, but most probably maybe in the tutorial session I will do that one. Okay? I will open the Proteus. The Proteus is very self-explanatory. I will just give you a simple, maybe like a half-an-hour tutorial, and then the heaven is open for you. You can then just go on and understand whatever you want to do it. In fact, Sir Bilal can actually take a tutorial session for that also. But don't worry, Proteus and all these simulation software, there are a lot of simulation softwares which are going to be coming your way in your next 1 year or so. So when we will connect the PCB to some microcontroller, how will our circuit be completed? I mean, where will we attach the ground? Of course, beta, ground has to be connected. Whenever I am going to connect these 4 wires and these 5 wires, I will need a ground pin. So this means certainly that my microcontroller ground and this circuit ground, which is exactly this white pin at this where my mouse is at present, this has to be confirmed. So ground has to be common. This is the first rule. I guess this will be taught to you in circuit analysis also, that your ground has to be common in whatever 2 circuits are going to be connected. If you give 15 volt input, what will happen? This regulator is at present working without a heat sink. Okay? And what is a heat sink? Let me just show you. I will just show you. Heat sink, as the name suggests, is actually a device which is actually going to dissipate the heat from the, actually trying to find out a heat sink for you. Let me just see. I have some. I don't know how many of you have opened your PCs or something like that, and a heatsink is something like this, as you can see, as like this. This is just a simple shape over there, or maybe this is actually, I have taken it from my AMD processor. That was my last PC, and actually it was faulty. It turned faulty, so I just took out this heatsink. You can see what is the purpose. The purpose is that the heat can be dissipated. Now, coming back to your question, if you are going to have input 15 volt to this regulator, you will require a heat sink, which will be certainly this shape. I will tell you that one also in your next experiments to go on, that you are going to attach this heat sink here at this, as I can show you this one. This is actually a heat sink also. So this heat sink will be attached at the back end of this. You can see the screw over there and also a screw hole over here. So when you are going to attach this one, the heat is going to be dissipated. So if you are going to give more than 15 volts, it's going to be more heated up. And if you are not going to dissipate the heat, you are actually going to turn this faulty, that's the regulator. And it will also even turn faulty if you are going to run it at more than 500 milliamperes of current. At present, it is only working at approximately 70 or 80 milliamperes of current, so it can work without a heat sink. But if I will go up till 400 or 500 milliamperes of current, I will require a heat sink, maybe of this shape as I have shown you, or maybe something like this. This is actually don't have any hole over there, but yes, I will have to attach a hole over there. It is a big heat sink, certainly not this much size. I will show you that heat sink also and its footprint in the, because then you will have to place a space for that one also. So I have not yet given you a heat sink, how those heat sinks are actually going to be used. So heat sinks are required if you are going to give it 15 volt. But a ULN2803 is a 16 pin. Okay? I don't have a ULN IC which is only having 5 inputs. ULN ICs come as a standard for 8 bits. So that's why I am using, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, sorry, 18 pin. Because these first are the 18 pins and certainly this one is the ground over here where my mouse is at present. So these are 8 bits over here. So this is an 18 pin IC, and same case over here for the dip switches. I told you last time also that dip switches are only available in 8 bits, 4 bits or 2 bits, or maybe I guess I found some of the bits also. Let me just show you. I have a little bit for, but they are not available at Hall Road. This is actually something very, I found somewhere from the, you can call it junk in our department. They were actually fixing this, and I found this one. Now this is a very simple thing, you can see it's quite colorful. It's a PCB, a dip switch, you can see. And this dip switch, as you can see over here, it's having almost all the colors of a rainbow. So you can see now how many are there, how many switches are there. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 are there. As you can see the numbering also over there, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0. So this is and it's of very good quality. I just found 3 or 4 of them. But again, it's not available at Hall Road, so you can't actually get a lot of them over there. And maybe if you import it from maybe some Western website, maybe you can get it. But yes, only dip switches are only available for 8 bits, 4 bit or 2 bit. Okay? So you have to adhere to that one. In our case, we only have 5 bits, so the rest of the remaining 3 are actually wasted. So anyway, they are still there in the circuit. Any other questions? Then I can. Roll number 19, I agree with your word. We should have placed a ground header for the microcontroller, but don't worry on that one. I can do that. We will do that when I will have that circuit running, and I will show you. I can just insert a ground wire over here in this white pin. Because I have a screwdriver, I can just unscrew and then I can put it. So adaptation, remember, I hope so, you are going to be working in 4 years in this department. Please adhere to adaptation. You have to adapt yourself to the surrounding. Now when I went to UET today in the morning, I was there, and in fact lab staff was also not there, they were on leave today. I completely got all this equipment from the lab, and I tried to solder it, and then I tried to clean it up and all that stuff. Maybe I could not find 1K resistance, then I used something 1.8K resistance over there. You can see these are not 1K. If you can zoom in this one, you will find out these are not 1K. But again, 1K or 1.8K, they can still serve the purpose, so nothing issue over there. So this can still work over there. So please try to adopt, and this will be also because you are again not a third world country, but again a second world country, and you will have to do some adaptation as this course and this engineering is going to be. Any other questions, or we can move on to the next? I don't know, Atib is there or not? Atib, you almost spoiled my hard work at least, because I was like, when the whole circuit was running and then I saw the switches arrangement position, I checked it before coming today from UET, but this was a big letdown for me. Anyway, don't repeat this mistake. Any of you who has done this previously in any assignments also, please make a habit, always have the least significant bit on any one side. It can be here, it can be here, any one side, left or right or wherever, but it has to be continuous. Don't, even if the IC is not giving you that, but do it in your tracks or whatever, so that the least significant bit on one side and most significant bit on the other side, so that you have this over here. So you can see over here what I have done. I have written A, B, C, D. What is A? As I told you previously also on your data sheet, it was A was D0, then B was D1, C was D2, D was D3. So this was the experiment number 3 over here. Okay. Okay, now turning on to the experiment. which is today. Now, our experiment today is involving a yellow dot matrix, and when I use the word yellow dot matrix, I will show you on the camera as well. Let me just take off this PCB which is running over here, and this is our dot matrix, and I'm showing you this one. Okay, so this is this yellow dot matrix. As you can see, there are 64 LEDs inside it. Okay, I hope everyone is listening me and my voice is there. You can see there are 64 LEDs inside it. It's a simple yellow color dot matrix, easily available at Hall Road, and it has 64 LEDs. Now, in a simple layman, if you are talking about 64 LEDs, this 64 LEDs are going to have 128 pins. Why? Because we know 64 LEDs are going to have 64 anodes and 64 cathodes. But they are arranged in, again, multiplexing, which means that you are going to have only, now you can see over here, and I'm holding this one in my hand, you can see how many pins are there. If I just count them over there, these are like 1, 2, 3, 4, 5, 6, 7, 8 here, and 8 certainly on this side. So you can see I have only 16 pins. So this means that 64 LEDs inside this one are actually being controlled over here by 16 pins overall. And this is a perfect square over there. And what is the advantage of it? Sometimes you want to actually make a screen. So when you are going to make a screen, let me just show you. I have some of these yellow dot matrices over there. So when you are going to arrange them in a screen, I am going to attach like this. And then I'm going to place another one here, and then I can build up the screen. Now this is only one color, so this is going to be not having a capability of showing you a screen, but your normal television, okay, normally, or your mobile screens, they all have pixels. I hope everyone has an idea of a pixel. You all normally whenever you want to actually buy a telephone or a mobile or a cell phone, you always go for which has the maximum pixels per inch, PPI. Many of you are aware of this one. Now here, this is also the same thing, but here the size of the pixel is very big. It's actually an LED, and when it's going to be running, it's going to be giving you yellow color only. Otherwise it can be a red or green or blue or whatever over here. Now our experiment only involves one of it, which means that, now one thing very important about this yellow dot matrix, as I told you, it has 16 pins, and these 16 pins are going to be numbered in this way. This is very important. Here you can see this is the name written. This name should be facing towards you. So when this is placed over here on the table or wherever on the circuit, wherever you're going to place it, pin number 1 is going to be this pin. Pin number 1 is going to be this pin, then pin number 2, pin number 3, pin number 4, 5, 6, 7, 8. So from pin number 1 to pin number 8 here, and then when you have placed it like this over there, from here pin number 1 to pin number 8, and then pin number 9, 10, 11, 12, 13, 14, 15, 16. So here it's the same thing. So 9, just like we have done the IC. So pin number 1 here, and let me just take on a little away from it. Yes. So pin number 1 here, 2, 3, 4, 5, 6, 8, and then 9, 10, 11, 12, 13, 14, 15, 16. So these are 16 pins arranged over here like this. So from pin number 1 to 8, and then from 9 to 16. Now how they are connected internally, let's go to the circuit diagram so that we can see over here what we are actually looking at. As I have told you previously also, that just like I showed you, the marking is here. Which marking here in our case, if I can show you again, the marking is something Tom-1988. This is actually just some code coming on from the company. You won't find its data sheet on the internet. That's why I have given you this data sheet over here. We'll just talk about this data sheet also. You can see over here that this is Okay, this is actually getting, okay, one thing, sorry, actually my mouse scroll button. So you can see over here, the marking is here, pin number 1 to pin number 8, and then from pin number 9 to pin number 16 over there. Now, this is the circuit diagram internally. As you can see over here, I have given you this circuit diagram previously last night also, and it's also available on the website. You can download it. You can see that these LEDs are arranged in a common anode configuration also and a common cathode configuration. But if you can see over here, all the LEDs which are in a column, this is column number 1, which means physically when I am holding this one, I am holding this one, since this is the name, as you can see over here. So this is my column number 1, this is my column number 2, this is my column number 3, column number 4, column number 5, 6, 7, 8. So I have from column number 1 to column number 8, and if I go back on my circuit diagram, this is my column number 1, this is my column number 2, this is my column number 3, 4, 5, 6, 7, 8. And as far as the rows are concerned, this is my row number 1, this is my row number 2, row number 3, subsequently to row number 8. And if I go physically, this is my row number 1, this is my row number 2, row number 3, row number 4, and subsequently up till row number 8. So I have 8 rows, 8 columns. Certainly this makes 64 LEDs over here. Now you can see column number 1, all the LEDs which are inside it, certainly they are yellow color, they are connected to pin number 16. So if you want to turn all the LEDs which are inside the first column on, you have to give 5 volt signal or something like that, whatever voltage on pin number 16. Similarly, if you want to turn on the second column, you have to give supply of 5 volts at pin number 2, and subsequently 14, 4, 12, 6, 10, 8 over here. But after giving the supply at pin number 16, 2 or whatever, you have to give a ground path, which means a sinking current path on pin number 7 or 9 or 5 or 11 or 3 or 13 or 1 or 15, so that you can on any of the LEDs. Now, if you want to display, supposingly on the first one, on the first column, you want to display only the 5th row LED. So you have given a 5 volt signal at this point, okay? And you will give a sinking current path at pin number 3. So what this means, that pin number 7, 9, 5, 11, 3, 13, 1 and 15, they are going to be connected to a ULN2803 IC that we have used in just the last experiment. We have used it to sync the current over there. And again we are giving a signal through a dip switch, same topology, nothing changed over there. Again an 8-bit switch, because these are 8 rows. So we are giving an 8-bit switch to supply on the ULN803, and here we are using some resistances. Why resistances? Because these resistances will limit the current which is going to flow from these one. So I've still not talked about the column, because on the column you have to put some transistors over there. So for those transistors you are going to actually connect it. We will just talk about it a little later. At present I am talking about the rows which are 8 over here, and those 8 rows are connected through resistances. That resistance value can be from 10 to 33 ohms, and they are again going to be connected to this one. One thing very important, since row number 1 is pin number 7, so pin number 7 either connect it with this O1 or either connect it with O8. It's totally up to you, but keep the sequence same, which means if pin number 7 is here, pin number 9 is here, pin number 5. So don't make it like 7 here, 9 here, 5 here, just like what Atif has done over here. So pin number 7, 9, 5, 11, 3, 13, 1 and 15. You can see I have written over here all the pins, and these are connected with this one. So pin number 7 to 15, or including all of these ones, through a resistance certainly in between to limit the current, they are connected with the ULN2803 IC, and again that ULN2803 IC is connected with a dip switch. Again, it's a 16 dip 16, and again there is no need of a pull down resistance over there, which means just like we have used those 1 kilo ohm resistances connected to ground, no need of that ones over there, because this IC has an internal ground insulate, because you are sinking the current, you are not supplying the current. So over here, and again you have to connect a male header. I have not shown this male header over here. This male header has to be connected on this 8 pin, certainly in between. One thing very important over here, if you see, if I go back on my camera and if I can show you this over here, one thing which I will want you to practice in your next PCB, whichever you are going to design, you see over here, this is the IC, this is the dip switch. Here the spacing over here between these two ICs is very small. Now I can put a female header or a female wire over here easily, and also here, but as far as you are concerned, when you are going to connect this circuitry with some microcontroller, the space may be a little small. So kindly, whatever space you are seeing over here, kindly increase it a little by maybe like 1 mm or 2 mm more over there. I am talking about this distance over here, and certainly this distance over there, maybe 1 mm here, 1 mm here, so that there is an ample space, so that you can connect a 4 pair wire and a 5 pair wire very easily over here. So kindly, in the next experiment, certainly this experiment number 4 or 5 which is going to come on next, kindly have some space so that you can attach some wire over here very carefully. So please don't put them just very close to each other. Yes, I know I always ask for the PCB sizes to be very small, as I have asked this Mr. Ateem and Taimur who have done this one, but anyway, have some space so that you can actually attach some. You can see the space is very small here and here. So this is going to be a difficult, but anyway, I can do this one very easily, and I will show you that PCB also. That microcontroller working. So this male header has to be connected over here on this 8 pins. Again, ground has to be connected to this ULN2803 IC, and this is the, so here from all the cathodes, you can see all the cathodes are common. You are actually having all these pins, pin number 7, 9, 5, 11, 3, 13, 1 and 15, connected through a resistance to a ULN2803 IC to a dip switch over here. G. Any questions with this? Then I will come on to the next. G. Any questions with this? Then I will come on to the, because I have to actually show this one on something else. Any questions? Please write down in the. Okay, I will repeat the data sheet over here. You have 64, just like this. You have 64 LEDs, and if I had 64 LEDs to be controlled, I will have 128 wires or pins coming out. Why? Because 64 LEDs mean that each LED has going to be one anode and one cathode. Just like this one over here, this LED, it has one anode, one cathode, but here they are multiplexed in such a way, or they are connected in common columns or common rows in such a way that you can see that all the LEDs in one column, they are connected, all of their anodes are connected over here, and it's connected to pin number 16, column number 1, which mean by this is the column number 1, as I told you. This is column number 2, this is column number 3, 4, 5, 6, 7, 8. So this means that all of these LEDs in column, they have their common anode at pin number 16. These ones in column number 2, they have at pin number 2. Then I have at column number 3 at pin number 14, and subsequently up till column number 8. Then if I come on towards the row side, their anodes, their cathodes are actually combined together again. So you can see all the row number 1 LEDs which are arranged over here, they are having at pin number 7, they are combined together. Then at pin number 9, for all the second rows which are 8 LEDs over there combined together. Then at pin number 5, I have for the row 3, and subsequently you can do it up till row number 8. Now, the advantage of having 64 LEDs connected to 16 pins over here is this, that you can display any data. Okay, this is actually just like a simple screen. Most probably I will share a video with you also, maybe in the WhatsApp. I will show you, maybe it's last year video, and I will show you, you can display anything on this one. It may be a digit, maybe something animation or something like that, A, B, C, D, any alphabet that can be easily displayed over there. Again, but by the same technique, that is that you are time slicing it, as Sir Bilal has just told you, that you are actually going to display maybe on the first column, you are going to display all of them on. And then firstly you're going to, on column number 2, you are going to display something in center over there, and then on the third column you are going to display something again, and then on the fourth column you are going to display something over there. So this all for the 8 are going to be displayed in such a fast way that when you are actually going to see by a human eye, all of these are going to be static in front of you. That's why, I don't know how many of you are aware of this, whenever you try to buy a mobile phone or maybe a TV or an OLED, you always try to find a TV or something which has a refresh rate of 60 Hertz. I don't know the feed is listening here or not, but the feed actually, I was asking for a 60 Hertz refresh rate for this video converter which I am using over here at present for the camcorder. Now having a refresh rate more means that you are updating the screen fastly. So similarly over here, I am going to refresh this whole 7 segment, oh sorry, not this dot matrix over here. If I am going to do it very fastly, the picture is going to be more clear to me. Okay? But yes, certainly beyond 120 Hertz, our human eye is not capable of actually capable of discriminating it. So don't buy a TV or something screen which is more than 120 Hertz. Our human eye is not capable of actually accepting it. Yes, it can differentiate between 30 Hertz and 60 Hertz refresh rate for mobile phones or whatever you're using, but otherwise it's not capable of working for more than that. Maybe 120, it's still there. So over here, I hope this question is answered over there. We will share it, number 185, we will share. Sir Bilal will share the library also over there, that very simple library. I have made it customly over there. Okay, now coming on to the columns, the most important thing. Now here, this is 2 transistors. Now one very important, I don't know how many of you still remember your FSC, this is not a Darlington pair. One thing very important, this is not a Darlington pair transistor over here. This is not a Darlington pair transistor over here. This is a high-end switching circuit over here. Now, listen this very carefully. Meanwhile, I will actually try to have some whiteboard also arranged over here. Actually, I want to show you if I can make it available. Okay, let's see. Okay, now meanwhile I will try to have my mobile used over here. Maybe if I can do something on this one. Okay, now how the circuit is working and why I am using this circuitry. If you remember your experiment number 3, here your power or the current was being supplied from F, G, A, B, C, D, E. And this was provided to any of the 7 segments over there which were common cathode, and then the current was sinking in this ULN2803 IC, and then there was the dip switch over there. Now the current which we are talking about is a little large. I can't use that IC because that IC is actually there for displaying something. Here I have to actually have a lot amount of current which is going to be available to the dot matrix. Now for example, if I'm talking about this dot matrix can easily go to something 200 milliamperes of current or even plus than that if all the LEDs are turned on. So I have devised over here a 2 transistor approach, and how this transistor approach is working, I am using that same 2N3904 transistor to turn on another transistor which is 2SA684. In fact, let me just bring that 2SA684 transistor also. I have, I guess, over here with me. I have 683 at present with me. It's almost the same thing, just a little bit difference in the voltage over there. If I can show you on camera, this is that transistor 2SA684 or 2683. You can search its data sheet over there. The shape of this transistor is almost the very same, just a little bit size increase, but overall you can use the same footprint. Now, what this transistor is going to do, if you see the data sheet or the circuit diagram which I have given over there, 2N3904 was an NPN transistor. That was an NPN transistor over there. And 2SA684 is a PNP transistor. You can see by the arrow also, which I've used over there. This is a PNP transistor. And for those who have a problem over here, let me just search on the data sheet over there. Let me just turn on the recording. Okay, so 2SA683 or 684 data sheet is there. You can see over very carefully over here. This is a silicon PNP epitaxial planar type. Don't go with this planar type and all that stuff. This is actually depending upon the construction, how this is actually working. Now, the important thing of this transistor, if you compare it, now I will compare this one with 2N3904 data sheet. Now, I will compare this both data sheets over there. If I scroll down over here, 2SA683 has 30 volts, 2SA684 has 60 volts. Now don't confuse yourself with this negative sign. Negative sign is there because this is a PNP transistor. If you are going to see at 2N3904, you will see always positive values. Over here you can see the collector emitter voltage or collector base voltage or emitter base voltage. They all are positive. But if you will see a 2SA683 or 684, they are 30 volts and 60 volts. Now our circuitry, in our case, this is not going to work more than like 9 or 10 volts. So in our case, 2SA683 is going to work fine. Now the interesting thing which is here, if you see the peak collector current, the peak collector current is minus 1.5, or ignore the minus sign at present, it is 1.5 amperes. Now this is the peak current, which means that there is going to be a peak one, but the normal current of this transistor is 1 amperes. Now this is a huge increase from what the value of the current that this could supply. 2N3904 was only capable of supplying 200 milliampere. Now 2SA683, it's a PNP one, but it can provide 1 ampere. Now why we need it? Because when we are going to supply current through this black wire to column number 1, again I am going to supply from this PNP transistor to column number 1, which is pin number 16, which is pin number pin number 16. This current is going to be huge. Why? Because if each LED is going to take supposedly 10 to 20 milliamperes of current, so 20 milliampere of current plus all of them are on, this means 160 milliamperes of current. So this is going to still go on the large side. So sorry, on this one you are going to have a huge current over here. So that current has to be provided through a PNP transistor. Now why I needed a PNP transistor? This is very important. If I wanted to turn this on, okay? If I wanted to turn this PNP transistor on, what I will require? I will require, because this is the emitter over here. Remember, this is the emitter. Wherever the arrow is there, I hope you remember this thing, wherever your arrow is there, you are going to have the emitter at that point. So where your emitter is there, your current is going to flow inside. Now, if you remember your basics of your transistor, how you turn on a transistor, you have a base emitter junction forward biased. Base emitter junction forward biased. Now you know, for a 2N3904 transistor, what you are doing? You were providing 5 volts from a dip switch here, or maybe in the previous cases, and you were giving 1 kilo ohms, there was a base resistance and base emitter was forward biased and there was a current flowing. So what will happen now for a PNP transistor, this is opposite logic. So from emitter to base, current can only flow when this transistor is turned on. I am again repeating. From this emitter, this is the emitter where my mouse is at present. From this 10 ohm resistance, current can flow towards ground or towards the base and then flow towards this transistor towards the ground only when 2N3904 transistor is turned on. If it is not turned on, what will happen? Since this is connected to 5 volts and there is a 4.7 kilo ohm resistance and the other end of this 470 ohm resistance is open, it's not connected to anything, because if this transistor is not turned on, it's working as a switch, so the switch is turned off, so this is open. So the base of your transistor of this 2SA683 or 684, it is going to be a 5 volt over there. So current cannot travel from a 5 volt through a 10 ohm resistance and then back over there. Practically not possible, because you all know current always travel from a higher potential to a lower potential. So the only way possible that current can flow from this emitter towards the ground path when this 2N3904 transistor is turned on. So what you mean by this, that you are going to give a 5 volt signal from maybe a dip switch over here. The base is supplied with 5 volt. Emitter is already connected with ground. So what will happen? This transistor will turn on. The switch will be turned on. So now what will happen? The current is going to travel from this 10 ohm resistance towards the base of this 2SA684 and then through this 470 ohm resistance. This can be value 390 or 330, whatever. That's again a design procedure. I'm not going to talk about that one. So the current is going to travel from this one towards this transistor and then travel to the ground. Now as soon as this will travel towards the ground, this transistor will be turned on. So when this will be turned on, huge current can flow from this 10 ohm resistance directly inside the collector. Please remember that from your emitter to collector, in PNP transistor, current always travels when it is going to be a turn on switch from the emitter towards the collector. As the direction of the arrowhead shows, this is going to travel over here. So from the emitter to the collector, current is going to flow and then it is going to be available for all the LEDs in the column number 1, which is pin number 16. So, and when you are going to turn off, what will happen? You have turned off, 2N3904 transistor turns off. The current which was flowing towards from the emitter over here towards this one, that current is going to be very small. And this 470 ohm resistance is there to limit that current. Otherwise, this current is going to be huge. So this resistance 470 ohm is only there so that it can limit that current which is turning on this resistor. Now as soon as 2N3904 transistor is going to be turned off, again 5 volt is going to be here because of this VCC of 5 volt over here, and 2SA683 or 684, they will be turned off. So by using our NPN and a PNP transistor, what you have done, you have turned on the current for your column number 1, or you are going to repeat this circuitry where my mouse is hovering. You are going to repeat this circuitry for column number 1, column number 2, column number 3, 4, 5, 6, 7, 8. Which means that this circuitry having 2SA684, 2N3904 and 1, 2, 3, 4 resistances is going to be repeated 8 times. I'm again repeating, this is very important. I have only shown this circuitry here for the column number 1. This same circuitry is going to be repeated for column number 2, 3, 4, 5, 6, 7, 8, which means connected to the collector of this 2SA683 or 684 is going to be connected to pin number 16. Then you are going to repeat this circuitry, connect to pin number 2, repeat this circuitry, connect to pin number 14, and then subsequently pin number 4, 12, 6, 10 and 8. And the input of this ULN2904 having those 1 kilo ohm resistance. This is going to be connected to those 8 dip switches over there. And you are going to add a pull down resistance of 1 kilo ohm at the input over there, just like you have done it previously, and a male header. This male header would be at this point where this was, just like this circuitry. If you remember this circuitry over there, you had this over here, the male headers over there like this. So again, male headers like this between the dip switch. Here in our case, this experiment, you don't have a ULN2803. ULN is on the other side over there. So you have this experiment number 4, in which you have this high side switching. Now, why this is called as high side, I will just give you a little brief overview. Let me just on my whiteboard at present, then I will tell you. Meanwhile, anyone has any questions, please ask me now. Write down in the conversation window. I'm just okay. I hope you can see now. The question asked over here is this, that how the pins are different, or what I am talking about. Now, if you see over here on this one, I'm going to show you this one over there. This is the name. I will just use my pen and all that stuff over here. You can see this is the name written. So this means that only this is pin number 1, 2, 3, 4, 5, 6, 7, 8, and then I have 9, 10, 11, 12, 13, 14, 15, 16. So when you are holding it like this over here in front of you, so certainly this means that this is my column number 1, this is column number 2, column number 3, 4, 5, 6, 7, 8, and row number 1 is certainly this one, row number 2, row number 3, row number 4, row number 5, 6, 7, 8. So this means that all of these are arranged over here. But if I move on towards my circuit diagram, our circuit diagram has been shown in such a way that column number 1 has been shown here. Okay? So don't worry on this one. This LED at which my mouse is hovering is exactly over here like this point. Okay? So it's just the way, because the LEDs are arranged in such a way that this is pin number 16. Otherwise, this pin number 16 could have been shown down. It was just reversed down, and then row was also down. So it's not like that physically this is the shape over here. This LED where pin number 16 and pin number 7 are going to be energized, this is this pin. So this is column number 1, this is column number 2, column number 3, column number 4, this is row number 1, row number 2. So it's just the way how this is actually being explained over there. Otherwise, it's the very same thing over there. So I hope this is understandable. Anyway, actually, I don't have actually, so I will just use a piece of paper and over here. So I hope. You can have the idea what I'm actually trying to do over here. Okay, now what I'm doing over here is this, that I have high side switch and low side switch. I hope I will hopefully next time I will have that turned on. Actually, I have my stylus pen and that's not actually interfacing with my desktop at present. Now, you all know, please listen this very carefully. This is a very important part of because you are going to actually understand what I actually mean by high side switch and low side switch over here. Now, you all know a transistor is something by which you can actually use for switching purposes. So, when you are going to use your transistor for switching purposes, and you all know your transistor is going to be having this symbol. You are already familiar over here. And I hope this is not, if this is not visible, then certainly I will have to use some. I hope this is visible. So I have this one as collector, this one as emitter, this one as base. This is an NPN transistor. Okay? And if I want to make a PNP transistor, certainly I am going to make the arrowhead here like this, and then I am going to make it like this. Again, this is the base. This time this is emitter, this is collector, this is my PNP transistor over here. Now, as I told you, whenever you want to turn on a transistor, your base emitter junction has to be turned on. Which means that over here, if I want to turn on my base emitter, I need to provide a voltage of at least 0.7 volts so that a current can travel from this point to this point. And similarly, I need a potential between this emitter and base of 0.7 volt, or actually a current flowing, so that I can use this one as a switch and the current is flowing in this direction. When you are having these two transistors, well and good, no issues, the system works fine. But when you want to turn or use these two transistors as a switch, now, when you want to do it as a switch, now, if I have an NPN transistor, let's just see, I am making another NPN transistor and I am connecting the emitter to ground over here. Let me just make this one a little up. And on the base, I am attaching a resistance. This is a base a little thoda palag gaya. And here I have some LED or something which I am going to call as load. And here I am going to connect it as supposedly 12 volt or 5 volt or something like that. Now, what is I am doing over there? I want to turn on, this was some bulb or some DC LED or something like that I wanted to turn on. So I will give a 5 volt signal over there. A current will try to travel from the base towards the emitter, because this is emitter, this is base, this is collector. This base emitter will be positive forward biased. A current will start to travel from the top to the bottom and the load will be turned on. Well and good, no issues. It's very good. Now, this side type of switching where the switch is connected with the ground, this is very important, the switch is connected with the ground, this type of switching is called as low side switching. Why low side? Because the ground is certainly at a low potential, so your transistor which is working as a switch is working at low side. So that's why it is called as a low side switch. Now let's see, if I now connect the same transistor in such a way, this is connected to again plus 12 volts, and sorry on this one, my phone rang, and then I have a load connected over here. This load can be some LED bulb or some resistance or something like that, and then I have a base resistance again, and I am going to, this is the base, this is collector, this is emitter. Now, this type of switching is called as high side switching. Why? Because the transistor which you want to use it as a switch is now connected to the high voltage side. So now when you are going to give 5 volt, now here actually is a tricky part. When you are going to give the 5 volt signal, what is going to happen? The current is actually going to travel from this base emitter through the load towards the ground. Now, if the load, listen to this very carefully, if the load is going to not allow a substantial amount of current and the voltage which you have provided over here is not adequate, so the base emitter junction will not be turned on. But if the load allows that one, which means that the load is small, which means the load is having not much resistance over there, so what will happen? 5 volt is going to be over, base emitter junction is going to be turned on, and you are going to have the current flowing. So this is high side switching. This can work up till a certain point when the load is small. But here the case of a yellow dot matrix, you cannot use a yellow dot matrix because here the currents are huge. So what we have done over here, I have given you a circuit diagram in which you are having a NPN transistor over here, and that is connected through a resistance and then another resistance, and here this is connected as like this, and this is again a resistance, and this is connected to that 5 volt. So now what is going to happen? This is an NPN transistor, this is a Pnp transistor, and you are going to connect to load over here. Load means whatever you want to turn on and off. So when I am going to give 5 volt, current can easily flow because there is a ground connected. Here there was a load connected. So it was not easy. So this circuit for here can only work when the load is small and you have something like a very small 7 segment, then this circuitry can work even at 12 volts or 5 volts, something like that. But when you are having something like this where the load is a little large, then and you want to connect the switch, which here the switch is at the high side because this is connected with 5 volt. So this transistor is going to be turned on by a 5 volt through that dip switch or that microcontroller, and here you are going to have this as 470 ohm. As I told you, this is going to actually have the current limitized, and here this is just 4.7k or 3.9k resistance, so that a 5 volt signal is available over here when this is turned off. As far as the working is concerned, please say this very carefully over here. If I am going to turn on at 5 volt, this transistor is turned on, current can flow from here to here. So what will happen, from this emitter to the base, current is going to travel through this 470 ohm resistance through this NPN transistor towards the ground. So what will happen, it will be turned on. This PNP transistor is going to have the current supplied to the load. Now when as soon as you take this off 5 volt over here, now this is 0 volt, the transistor turns off. When it turns off, you are going to have this current disrupted. So what will happen, this transistor will be also turned off. And as soon as this is gone to 5 volt again, this will not have any current flowing over here. So the emitter base junction will again be reversed biased. I hope everyone has an idea about reverse biased and forward biased from your diode knowledge and transistor knowledge. So this type of switching is called as high side switching using a PNP and an NPN. This is certainly not a Darlington pair. Please, this is very important. This is not a Darlington pair over here in this way. I hope you have got the idea what I meant by high side switching and low side switching. I'm sharing a small link with you in the chat window. It's a very good link as far as the concerned high side switching and the low side switching is concerned. So you can learn a lot from this high side switching and low side switching from this link. Those of you who are saying the video is stuck, I don't know why. From my side actually it has been completely okay. I actually wanted to show this on my stylus over here, but anyway I will try next time, hopefully that this turns on and over here. I hope so. The link and this 5 volts, the high side switch, the low side switch, and all of this what I have tried to explain over here is okay. And this experiment which is over here, again a yellow dot matrix running from high side transistor switch and ULN2803 IC, and make sure that this yellow dot matrix is at the center of your PCB. This is very important, your center of your PCB. And those of one of you who are actually asking me that where you have to connect your pull down resistance, if I make the same transistor again, let me just make that transistor again. This is that ground connected, this is that base resistor, and then you have that resistance again, then you have a resistance again, and then this is actually going to be like this and like this, and so this is from actually there is a resistor here as well. This is plus 5 volt, and this is your collector, this is your emitter, this is your base, this is your collector, emitter, base, and over here this is connected to your load. Now those of you who are asking me that where you are going to pull down the resistance, your dip switch is connected here. So you have a switch over here, 8 dip switches over here, this is connected with this one. So when you are going to give a 5 volt signal, it's going to be provided. So a pull down resistance is going to be connected here between the ground, like this. So I hope you get the idea what I mean by that over here. So you have provided a 0 volt signal. So this transistor will not turn on. So if you make it open and this is not connected, supposedly the dip switch is not connected, so this is a stray voltage can occur anytime in the circuit and this can be turned on. So this circuit will be turned on, this PNP transistor will be turned on, and NPN transistor is going to be on by a stray voltage, maybe for just a fraction of a second. So this is that pull down resistor. This is that pull down resistance, and since you are going to repeat this whole circuitry 8 times, and this is going to be connected to the column. So you are going to repeat this one for column number 1, you are going to repeat this one for column number 2, column number 3, column number 4 up till column number 8, and certainly all of them are going to be connected to this dip switches, and you are going to have a male header at this point. Okay, so you have 8 pins over here on this point. So even if your dip switch is not working, you want to give it through a microcontroller, so those 8 pins are going to be. And one thing very important, your size of your PCB has to be something in between 90 cross 90 mm. This is the size limit for this single-sided PCB. This is a single-sided PCB over here. And for single-sided PCB, you have to make it in 90 cross 90 mm. Better, smaller, it's much better if you can make it, but 90 cross 90 mm is the limit for this PCB. And this circuit diagram, which is here in front of you, I have given you everything in this circuit diagram. The yellow dot matrix footprint has been shared with you. Sir Bilal has also given you the link also for that. The 2 transistors, as I showed you, they are going to use the same transistor packaging TO92 which we have used in the previous experiment. The only thing new in this experiment is this, that this time you are using 2 transistors over here, and they are actually connected in such a way that it's working as a high side transistor switch over there. Kindly go through the link which I have given you in the conversation window so that you can actually have an idea what I mean by this. Any questions, beta? It's already 3:30 and I wanted today's session to be a little smaller, but anyway, this has gone still up till 3:30. Any questions, beta? Please write down any questions over there, and बिल्कुल बेटा, you are, of course, you are allowed to use jumper wires for this assignment. Of course, you are allowed to use jumper wires. Again, the same thing. This is like approximately the last one, the last assignment with single layer. Hopefully, from the next one, we are going to move towards 2-layer. And actually, 2-layer PCBs are very easy to design for a designer. But when you are going to, as I told you previously also, they are very difficult as far as the cost wise is concerned, and their manufacturing is a little difficult. So that's why I normally just for first year and second year students, or even for third year ones, I normally advise them to always design single layer PCBs, and then maybe for your final year project or something like that, or you are building something space constrained or something like that, maybe then you can have a 2-layer PCB, or maybe more than that. We will go on towards the multi-layer PCBs also. Yes beta, 470 ohms and 10 ohm both are connected to VCC or 5 volt. Again, the position of this 470 not sorry beta, I guess you have written it. No, they are not connected. It is 4.7k beta, 4.7k and 10 ohms. They both are connected to 5 volts. 4.7 kilo ohms and 10 ohms. They both are connected to 5 volts, and 4.7 kilo ohms other end is connected with the base of 2SA684. And please don't take any problem in actually using this 2SA683 or 2SA684. If you have this data sheet, please see the data sheet. you have emitter, collector and base. So this is emitter, collector and base. And if I can show you on the camera, I have this transistor here in my hand, and if I have this one, these are the 3 pins over here. In fact, let me just place it on this paper, and then I can actually zoom in over there. So this is my, so I hope you can have an idea. And here what I mean by that, if you are actually holding it, so when you are holding it, pins towards you, this is the pins towards you. So when you are holding it like this, as I am holding it at present, let me just show you in the camera. So when you are holding it like this and your transistor is like this, so pin number 1 is emitter, pin number 2 is collector, then pin number 3 is base, which means that here when you are holding it like this, this is emitter, second one is collector, third one is base. Emitter, collector, base. I hope I have not done something wrong. Yes, emitter, collector, base. So this is emitter, this is collector, this is base, and these pins are facing towards me. The cut is away from me as shown over here. You can see this one as I'm holding this one, the transistor. This is very important. Please don't miss this part, because when you are actually going to try to solder this one on your PCB, this will be a difficult thing at that time. So don't do a messy thing over there, because if you will connect it wrong on your circuitry, then certainly the circuit will be not just not working, but the transistor will be also get fried. So this is very important that you understand how to see the data sheet and how to understand that which is emitter, which one is collector, which one is base. So this is emitter, collector and base. As far as TO92 packaging, again the same packaging as we have done over here.